Good evening, everyone. I am Haripriya, PhD scholar from IIT Tirupati. Welcome to today's course, Week 1, Digital Electronic Circuits. So, my screen is visible and right. Okay. So let's begin today's section. We will start with the basics of the switching circuits. So in digital electronics, we will be starting with the switching logic circuits. So in digital, we will be using the binary values which are having logic 0 and logic 1. So we will be designing circuits which will be operating with these two values. So now let's start with some basic one of the switching circuit. Let's start with an AND gate based realization. So we know V1, these are the two inputs, and we have an output, say V0. Now this we call it as truth table, or either you can represent 0 or it is logic low, and 1 represents logic high. So this is the symbol of AND gate, V1, V2, V0. So in AND gate operation, when both the inputs are 0, output is 0. For any one of the input is 0, output is 0. When both are 1, the output is 1. So to obtain operation equivalent to this truth table, using the switch, we can get, if we have a 5 volt, say, VCC supply, we need 2 switches. So this is one switch, we need 2 switches. And the input, the switch input will be, because we have 2 inputs. This has 2 input and 1 output. So now we have to make use of these 2 switches, and based on the connection, whether it is parallel or series, we can get the required operation. So now we want to design an AND gate. So we have a 5 volt supply. When both the switches are on, the output is 1. So now if this switch is on, the output here will be 5 volt. Again, this switch is also on, then this will be propagating here. So here we can get the Vout value, and this potential can be our ground potential or VSS, and this switch we can apply a V2 potential, our second input, and this will be our first potential V1. So now if V1 is equal to 1 and V2 equal to 1, then this switch will be closed, this will also be closed, so there is a path, so output will be 5 volt. If any one is 0, then this switch will be open, but this switch will be closed. there will not be any path from this. There will be path from here to here, but this path will not be there. So the output potential will be 0 volt. So if my V1 is 0, if my V2 is 1, then this switch will be on, this switch will be open. So here there will not be path. From here there will be a path and this will be at ground potential. So V out will be 0 volt. So we have obtained the AND gate operation. So here we have connected two switches in series. Now to obtain the OR gate operation, so again we will write the truth table for the OR gate. V1, V2, V0. So again 0, 0, 0, 1, 1, 1. So all the four combinations we have applied. For OR gate, this is the symbol V1, V2, V0. Again, this has two input and one output. So for OR gate operation, 0 or 0 is 0, 0 or 1. Any one input is 1, the output is 1. So now again, we need two switches. As we have two inputs, and then now again we will have a supply voltage, there is 5 volt, and I'm connecting my first switch here. So now when this switch is on, the output will be 1 volt. So again, if another switch, you need to connect it in parallel, because now if any one of the switches on, like if V1 is 1, this will have a path, or say V2 is 1, then there will be a path from here. So CO will be 5 volt for both this logic values. And then if V1 is equal to 0 and V2 is equal to 0, then this switch will be open, this switch will be open. So the V0 will be connected to the ground potentials. So for this, V0 will be 0. So any doubts still here? We have realized two logic operation and then or using the switches. Now I will use a diode to obtain this. I will use a diode as a switch and I will obtain this AND gate. So this is the logic operation which I am going to implement using the diode. We need a resistance to get the draw, so 5 volt. Now A and B. Now if AI is 0, then there is a path from here to here. So the output will be the diode draw, which is 0.7 volt. which is equal to 0 logic, and any one or both are 0, and A and B, when both are 1, this diode will be off, this will be off, so there is a path, and then the output will be logic 1. So in this way we can obtain the AND gate operation using the diode. So we are using diode as a switch. The second, to obtain the OR gate operation using the diode, the same connection, I will just reverse the diode. Instead of connecting to VDD, I will provide a path through discharge to ground by AB. This can be V1, V2 because we have used this symbol. And now, if any one is 1, this will provide, take some 0.7 drop, and this logic high will be 5 volts, so it will be like 5 minus 0.7 drop, which is 4.3 approximately, like it's a logic 1. When both are off, then there is a path, so it will be logic 0. So in this way we can realize a OR gate using a diode. Any doubts till here? Any doubts? If no doubts, we will proceed. We will cover some theory portion, then we will solve some sums. So now, when we are using a diode, we are able to get the operation for an AND gate or OR gate, but we were not able to obtain the logic for the NOT operation. So we will use transistors as a switch to obtain the NOT operation. So first we will realize an inverter, which is NOT gate. This is the symbol of the NOT gate. And the truth table. Zero output will be 1, 0. We will consider one BJT transistor. This emitter, collector, and one collector resistance. 52 VCC. Here, base resistance VM. So this will be providing inversion. So now if we try to draw the characteristics of this output versus input. So this also will be in volts and this will be in volts. Okay, we will first draw the characteristics, then we will discuss the regions. Okay. When we have 0 volt here, this will be in off state, so the output will be high potential. Then slowly there will be a conducting path and it will have a path to discharge. So this will have 3 regions of operations: cutoff, active, saturation. So this potential is the VIL, means till this potential, if you apply any other potential, like say 0.1, if it is say 1 volt, any voltage here will be considered as logic low and the output will be logic high. So VOH. And any potential here, it will be start considering as logic input as logic high, and this is output low. So now we will consider this region. Here it is the end of the cutoff region. In this region, you can see this current IB current is 0, like negligible. So still this VB potential is less than 0.7. So this transistor is in the cutoff state. For this complete entire region, and has the VN is increased beyond the 0.7, this base potential, it will start to conduct slowly and you will get a path to discharge to ground slowly. So when it is in the active region, in this region, the region 2, you will see there is a path. Now this IB, if you take this compound, this VN RB and this VB, we will obtain the IB current as VN minus VBE on divided by RB, and the IC is, you all know, beta IB, and the V out potential, this potential is VCC minus IC drop, this current IC drop. So this VCC minus IC drop. So this is the minus beta FIB RC by substituting all these equations. So substituting the ICF beta IB. So this is equation 1. Let this be 2. Then next, V out is now VCC. We know what is the value of IB from the equation 1. So beta F RC, and substituting the equations, it is V in minus VBE on. Okay, so you can see there is a negative slope beta F RC by RB. This is the slope. This negative slope indicates it's a discharging. Okay, so and we have taken VBE on here. Now if we come to this region 3, this is the region of end of the saturation region. So this point, this coordinate is 0.7, 5 volt, because once this VB is 0.7, this will start conducting. So this input can go up to 0.7 with the V out as 5 volt. So this is the coordinate, and this potential we will derive this. So we are in the saturation region. So this is our region 3. So in this region, the IC at this end of the saturation region, you can see this current. VCC minus VCE sat by RC. So VCC minus VCE saturation by RC. So, and this we assume to be 0.2 for our hand calculation, and this is 1. If we consider, then 4.8 milliampere. And then IB at the end of this saturation will be IC by beta. So this condition you know, like in the saturation region, IB is IC by beta F. So it is 4.8 upon 50. Beta yes, if you assume to be 50. So like for the hand calculation, in this we will consider some of the values, like we need this RB, which is 10 kilo ohm. RC is 1 kilo ohm. And then this beta forward 50. And we are considering both VB on and VB is set to be equal to 0.7. And then VCE saturation to be 0.2 volt. This VB saturation will be slightly higher than the VB on, but for hand calculation we are considering both to be 0.7. So now from there we have these values, and then this will be, so what is the input potential at this end of the saturation is VBE on plus this current IBRC. So VBE on plus IB at this region into RB. So it is 0.7 plus 0.096 milli, this one, into RB is 10K, is 1.66 volt. So at this potential we are getting 1.66 as the input, and this output we know VC sat is 0.2 volt. So these are the regions of operations, the 3 regions. So now let us take one question. We have given the sim circuit. This is the, okay. Can anyone answer what is the circuit operation of this given circuit? We have seen the circuit now. Any answers? Hmm. Okay. Okay, we will discuss the regions. First, what is the,
Saturation region.
yes, what is the functionality of the circuit, the operation of the circuit? This is an inverter. Because if it is, if Vn is 0, then this was in cutoff state and the output was 5 volt. When it reached 0.7, it started conducting slowly, and we were in the active region, and this started dropping, reducing till 0.2 volt. So this was the inverter BJT. So now they have given IB is less than or equal to IC upon HFE. So this is in the saturation region. Next, we will discuss the noise margin. So we have seen that VIL, VIH, VOL, and VOH. That okay, till this potential, if I apply, it will be considered as the input will be considered as the logic low. And same way, if I apply some potential within this VIH, it will be considered as logic high. Input has the logic high. And the same way for the output to be considered as logic low and output has the logic high. So the noise margin, if we consider this for the output,
Excuse me, ma'am.
yes, yes, sir.
Ma'am, that output alone, can you please repeat, ma'am?
This one,
No, ma'am. In this one only, that output part, ma'am. Not this one. The current screen we were seeing. In that output low, output high, that part alone, can you please explain, ma'am?
here if input is zero, the output,
No, ma'am. Current screen we were seeing in noise margin. Yes, ma'am.
yes,
In
yes,
this one,
yes.
OL and OH.
Okay, OL and OH.
Yes. This one logic. Can you please explain, ma'am?
Yes, yes, yes. So if we are applying any potential in this range, if it is an inverter circuit, we will get it will be detected as a logic low, and the output will be logic high. So output
Yes, ma'am.
logic high, and the same way, if we apply the potential in this range, if it will be considered as logic high, input logic high, and the output will be in this VOL range. So uh, now I will like brief it with this graph of both input and output. I think then we will get, if we have the input, then till this, if we will consider as logic low. So this is the output logic low. And in the output, if we say that okay, this much is the potential we have, it will be considered as logic high. So this region, we call it as the logic swing. So this swing you can see in this one. The swing is, it is going till 0.5 till 0.2. So the swing for this logic swing is point, 0.2 volt to 5 volt. And
Ma'am, I have doubt in this numerical.
which numerical? This one,
The transistor.
this one.
In this, what would happen if IB is less than or equals to IC by HF?
IB is less than or equal to IC by HF.
IC max.
It will be in the active region, right?
Okay, if it is IC minimum, what will happen?
Till this potential VBE is 0.7 volt. Till that it will be in cutoff. After that, if this current is sufficient, it will be in the active region. And once we have the current greater than or equal to IC by beta, it will be in saturation.
So there will be no IC minimum. right?
I see minimum means if you can say the value, then we can say, I think so. Yes, minimum I have not seen. Maybe next class I will confirm that.
Okay.
I will confirm if with IC minimum in the next class. With minimum current, I am also not IPs. Yes. So for the noise margin for the input portion, this will be VIL, and this we consider as VIL. So in this region, it will be considered as logic 0, and in this region, it will be considered as logic high. So this region is this transition width, and from here to here, this region is our noise margin high, and this region to this region is our noise margin low. So we have NML, noise margin low, which is VIL minus VOL, and noise margin high, which is VOH minus VIH, and this TW transition width is VIH minus VIL, and this logic width is VOL minus VOL. Our previous case, if we consider this as 0.7 minus this VOL was 0.2, it will be 0.5 volts. At the end of the calculation, we saw this value. So for the transition width, we know this was 1.66, and the logic high, we were getting from 0.5 to 0.2. So this is our logic side. This is one problem from the noise margin. Before solving this, let me okay. We have seen VIH is greater than VOH is greater than VIH, and VIL is greater than VOL. So it is like usually VOH is greater than VIH, and this we can call as minimum, and VIL the maximum point, and then VOL maximum point. And one more is we will have two noise margins, and noise margin low and NML noise margin high. So the overall noise margin minimum of NML comma NMH. So this will be overall noise margin. This problem.
One second, previous slide, please, ma'am.
Yes.
N margin. Thank you, ma'am.
Yes. We say this as minimum because you can see here, this is the minimum point and this is the maximum point. Here, this is the minimum and this is the maximum. Then we give these conditions. So, can you try this problem? They need output voltage. So, here it is output and high voltage. So, voltage is more and this is minimum. The next step from potential is for input high, so 2.8, and then voltage and this is output and it is low and max. Voltage is 1.5 and output it is input. See, high and low. It is a maximum voltage. It is 1.5. So can you tell what is high and low? Noise margin and noise height. So formula here is low is VIL minus VOL and this is minimum voltage minus VI height. Any other answers? Uh, 1.5 watts, 0.2, and this will be 0.5. What is the answer? Yes, the option A. Because it is the minimum of gates and control. Go to the next topic, fan out.
Ma'am, 1 second, previous slide, ma'am.
Yes.
Just 1 second, ma'am. Writing answer. VOH minus VIH. Completed, ma'am. Thank you, ma'am.
Fan out means if I say I have a logic gate, how many gates this current will be sufficient to drive all these gates. So number of gates that can be that it can drive. So for BJT, the current will be the limiting factor because for the base there is a current through the base. For MOSFET, the fan out calculation will be different. So here it is based on the current. So how much this current is and how much it is sufficient to drive how many gates. draw the circuit, BJT level circuit. Okay, I will. This circuit we have already seen. This is my inverter. Now I'm considering that this is the Vout, my previous output. Now this will be driving my next circuit. Say I am connecting another inverter. This one is already connected to VCC, so I can tie it here. And now this is the output. Like this, I can connect. And this will be my Vout. So how many circuits I can connect? So this will be dependent on, if I take that formula, this one driver base into the load current. So equation we can get IC driver is this region. So this current VCC minus Vout upon RC. VCC minus Vout upon RC. So we previously know that if I consider say VCC as 1.66 RC as 1 kilo ohm, then this will be 3.4 kilo. So then my IV load is this is the load V out minus V out minus this VBE by RB. Minus VBE this circuit equal to it minus 0.27 and VBE which is 0.66 and RB so it will be 0.96 milliamp. So if with this values my N value will be approximately 34. So I can connect 34 more gates at this output. And if you have some like noise margin, then the number of gates it will be reducing. So NF is here and then VO is here, and this will be as per the previous calculation. So I am writing that. So from this value, we will get IC VCC minus V out by RC 5 minus 3.66 by 1. Okay. Now my current is low because of this noise margin addition. And IV, which is the load, it is V out minus VB sat by RB. So 2.6 now my V out minus VB sat by RB, which is IC driver by IB load, IC driver by IB load. So you can see with this noise margin term addition, my number of gates I can connect has reduced. So NM this NPTEL reduces power from. So I will take one question.
1 second, previous question, ma'am. Yes, ma'am. Uh, 1 second, previous one, ma'am. This, yes, ma'am. This. Thank you, ma'am. Thank you, ma'am.
So now we have given that the non-relates will draw a current of 3 milliamps, and this current that can be sourced like from here is 10 milliampere. And can you see what will be the fan out? This is 10 milliampere. Each gets the 3 milliamperes, that is around 3. With this, it can drive these 3 leads. This is the propagation delay. So the every transistor will have a some delay because it is going to switch. So this switching of the transistor will give some delay. The switching speed of the transistor will give some delay. Plus some capacitances in the circuit. Plus the capacitance also. There will be the capacitance needs to charge and on while going from low to high and discharging from high to low. So this too will give to the propagation delay. And input also will not have an like directly go to like this input will not be there. So input will also have some delay. There also will be some delay. And if you consider this 50%, it will be called as propagation. Same way from here, this 50%, this 50%. This will be called as propagation delay low to high. And here 50% from output to input. So the propagation delay TPD is TP low to and high to low. And we have something called as rise time and fall time. This is from 10% to 90%, the delay time taken by the signal. And the fall time is from 90% to 10%, the time taken by the signal. Here we have 80% of input to output, 80% of the from 90 0 to 90% and 90 to 0%. We are taking the rise time and fall time for the output, then it will be for the output calculation. And this this also will be RC so if this is Vn and this is Vf, because of the circuit elements, this potential, this there will be some capacitances. So this capacitance need to be charged. So that will be the time, this charging time. And when this has to discharge, this is the discharging time. So it is the delay is dependent on this switching element plus this capacitor effect. So any doubts?
Only 1 second, previous page, ma'am. Ma'am, what is this TPD actually, ma'am?
It is the propagation delay,
Yes.
which is the average between the high to low and low to high propagation delay.
Ma'am, it is TPLH, ma'am. This
TPLH,
second, yes,
low to high.
yes. TR is
This is uh, rise time, the time taken by the signal to rise from 10% to 90%, and this is the fall time, time taken by the output signal to discharge from 90% to 10%.
thank you, ma'am.
So next, power. There are two types of power. Standard power, when the transistor is either in on state or off state, the power drawn, like the current drawn, it will be equal to the power. So the power taken by the transistor when either on state or off state. And the dynamic power, when the transistor is switching. It is defined by the switching speed. Okay. And we calculate something called as figure of merit using power specification into the propagation delay. It's called as figure of merit. Next, we'll discuss the architectures of electrical transistor logic. So we are having a NOR gate. So this is the symbol of the NOR gate, and the truth table for the NOR gate is 0, 0, 0, 1, 0, 1, 1. It is an OR gate with an inverter. So the OR will be 0 here, so it will be 1 here. The OR will be 1 here, so it is 0. 1 plus 0 is 1, so 0 for the NOR. 1 plus 1 is like 1 or 1 is 1, so 0 for the NOR operation. So if we connect two BJTs in this way, this connect to this RB, we apply one input. This is RB, another input, and for the pull up, we apply a resistor, and this is this is. So this is the, we have connected both BJT with A input and B input in parallel. So if it is 0, 0, This will be in off state, this will be in off state. So output will be 1. Okay. If it is 1, 0, this will be conducting. So there will be a path for this Y to go to 0. So it will be 0 in logic 0, but it will be in this drop 0.2. So in this way we can achieve a NOR operation using the BJT. So similarly, if we want to get an NAND operation, so this is the symbol for the NAND gate, A, B and Y, A, B, 0, 0. So NAND is actually the inversion here of the AND operation. So AND we will get 1 here, so you will get 0 here. The other values will be 1. So to do this, we will again connect the NAND gate here in series instead of parallel.
And will you get recording of this session?
Yes, we will upload the recordings. Yes, sorry. So another input, A input through this. And we'll connect VCC with the pull-up resistance R. This is the so this will be the output Y. So now if we consider both are 0, 0, then this will be in off state, this will be in off state. The output will be 1. The same way, if any one of the transistor is not conducting, like say this is off, this is on, or this is on, or this is off. So there won't be any path for Y to ground. So the output will remain in the logic high. And when both are 1, both the transistors will be on. So there will be a discharge path to ground. So Y will be in logic 0. Okay. So in this way we can realize an NAND gate using an resistor transistor logic. So now if we use transistors, this is the TTL logic, which is transistor logic. So we will have a multi-emitter like circuit. So we to apply the input, and this will work as the for the current steering, and this is the this resistance, and our circuit. So this will act as the input for this, and this will be providing a phase shift. Like here you have one connection, here you have one connection to one of the transistors. So this will be like making one transistor on at a time. So this will act like a phase shifter, and this diode will be providing a level shifting. So that it will ensure that when this is on, this is off by increasing this level of the potential. So this we will come to this question. So this one is called the multi-emitter transistor. So this will be acting like this will be used for, and this is our Q4 transistor. This we will discuss why we are using diodes at the input, and this is the diode D3. So which will be used
Ma'am, 1 second, previous circuit, ma'am.
same circuit.
Completed. Thank you, ma'am.
Yes, yes. So the multi-emitter, this one is providing the current steering, and this one is used as the phase shifter, and this diodes we will discuss this, and D3 will be used as a level shifter, and this one will be preventing this ringing effect. So usually also in diodes are used in the input circuitry to prevent the surge in the static the CMOS circuits. So this one is used for preventing the, so the answer is D. A is current steering, B is used for phase shifter 3, and D1 D2 to prevent ringing 4, and D3 for level shifting 1. D1 D2 is preventing from ringing. Like if I have say A, I am connecting it to a diode and grounding this. So this is the input diode. So because say I have an output, if I want to go to 0, instead of going to 0, there is some ringing effect. this diode will reduce this ringing and it will bring to the 0 and it will have like lesser ringing. So it will suppress the ringing. Because like this is at the reducing like this portion. So in this portion this will be negative, this will be at high potential, this will start conducting. If there is any ringing it will bring it to 0. Your doubt is clear? Any other doubts?
This will happen due to cutting voltage of diode.
No, once this, if there is a ringing at this portion, this diode will start conducting. And yes, it will maintain at the, it will provide a path to discharge to 0. Like not 0, this cut-in voltage, it will like maintain at the cut-in voltage. This will be suppressed. This ringing portion will be suppressed. Is your doubt clear?
Means why that would be suppressed.
Like there is a path to the ground. When this diode starts conducting at those at this region, it will have a path to the ground.
Okay.
Yes. So next we will discuss about the CMOS logic, and the CMOS is for metal oxide semiconductor transistors, where the gate is having an insulator. Like this will be the MOSFET and plus regions P substrate, and this will be the insulator and a gate terminal. So any potential we apply Vg, once Vgs is greater than Vt threshold voltage, say if it is an NMOS transistor, the channel starts to build. So we are using an enhancement type of MOSFET. In our circuits, like for our digital circuit. And yeah, this is the gate potential. This will be the, any one of the terminal can be source, the other terminal will be the drain terminal. So the CMOS circuit, because of this insulator, it will have a very high input resistance and hence it will draw very low current. Whereas BJT was drawing some input current, here there is no need, will be no input current drawn by this because of this insulator. And secondly, there the in the CMOS circuit, the fan out, whereas in TTL it was because of the current. Now in here it will be because of the propagation delay will be the limiting factor of this fan out. So
Ma'am, can you please say me roughly what is fan out, ma'am?
fan out, okay, if this is the any logic gate, here there will be, if we consider TTL logic, here will be some current, it will be delivering from here. So it can source some amount of current from here. So how many gates it will be able to source it? How many gates I can connect it here such that it will be, we can source it. So if this is going to take like some 3 milliampere current and it is able to deliver 10 milliampere current, then I can connect 3 gates at the output. So in the TTL, it was dependent on this current. So we had N as the because of this driver IC driver by the IB, which like here it was connected to the base. So IB load. Is it clear?
Yes, ma'am.
So in the CMOS circuit, this fan out will be limited because of the delay, because in here gate is not taking any current. So CMOS will have more fan out as compared to the TTL logic, and CMOS usually have high packing density, so this option is not there. And CMOS is generally faster than TTL. This also we can TTL are faster because here we have some capacitance. We have the charging of this capacitance. So CMOS has a very high input of this option is correct. It exhibits, it has more fan out compared to TTL, and CMOS exhibits lower power dissipation. In CMOS, we mean to say that there will be some network called pull-up network, and there will be some network called as pull-down network. This will be connected to ground, this will be connected to VCC, and output will be drawn from here. So if here any connection is in series, the equivalent connection here will be in parallel. And pull-up network we generally use PMOS, and pull-down we will use NMOS. So this is 1, 2, and 5, 6. So if we see briefly the NMOS base gate, like if I use only one NMOS, like NMOS alone, so drawing it like this. This is our enhancement type NMOS. I am applying a V in here. Now at the pull up, I am applying. This will be providing me some resistance. This circuit. This is it. So if we see the characteristics of this NMOS, it will be in the cutoff, then it will start to conduct. Once a pinch of voltage is reached, it will be in saturation region. So here it will be in the linear region, then it will reach the saturation region. Once you increase this VGS value, this is the ID current versus VDS. This will saturate at later state and then saturation. So if we plot this characteristics for this one, it will say threshold is 2 volt. It starts conducting. It exhibits a linear characteristics, so we can assume that this will provide the resistance, the pull-up resistance, but this will be limiting the swing, and we say that pinch of state, like the transistor into saturation when VDS is greater than or equal to VGS minus VT. So like we have this resistance which will be there in this charging part. So it is a slower process, and discharge is through this resistance which is in the on state. So this is a faster process. So now we will use, instead of this, we will replace it with the pull-up network made up of PMOS transistor. So generally here this input capacitance is 5 femtofarad, like for hand calculations from data. Our resistance is very high and output resistance is. So now if we are building a CMOS based inverter circuit, this symbol we can also simplify and use it like this. So this bubble means this is a PMOS circuit and it is connected to VSS. Gates we apply V in, this is V out. So this potential is VGS1 if we consider this is P1, P2, and here there is no bubble, so this is NMOS circuit, and this will be our gate to source potential. So we will see this. Circuit characteristics. We call transfer characteristics when we are plotting the output and another will be an input and both are in voltage. Sorry, this is here, both are in voltage. So let us apply some input till here. Let us consider. So when this region, it is 0 volt. 0 when applied here will turn on this transistor. This will be in off state. So T1 is in off state. Till this point it is in the region A. Then there is a further increase so that this NMOS starts to turn on. We come to till the region B. In this region T1 is in saturation, T2 is in linear region, not in saturation region. At this potential, we will come further down till C. In this region, T1 and T2 are in saturation. This region will be usually very small region where both the transistors are in the saturation region. And this potential is D. In this region, T2 is in saturation and T1 is in linear region of operation. Here, now when I apply 1, this will be off, this will be off, this will be on. So T2 will be in off state. So this potential will be when VSS minus VT. This is plus VSS minus VTP. And this region is when this delta V naught is based on this 2 threshold voltage. So this potential and anything else, yeah, this is will be in VSS state. Here minus VSS or say the ground potential. here it will be in the saturation. So this we can obtain this point as when the VO is equal to Vi plus Vtn 2 volt, and this potential VO, okay, wait, here T1 T2 is entering saturation, so this is Vi minus Vtp. This is Vi plus Vt minus Vtn. So this is minus 2 volt. If we consider Vtp for this, it is plus 2, and here it will be minus 2. These are the 5 zones. We have some current equations. When the transistor is in saturation region, the drain current ID is K times VGS minus VT the whole square, and in the linear region of operation, the drain current is K times 2 into VGS minus VT into VDS minus VDS square. I think I can write it straight.
I'm in that region 4. How did that T1 become linear?
Uh, in region,
Fourth region.
okay. In this fourth region, the potential is at somewhere here. So VGS should be greater than or equal to VDS minus VTN for the NMOS to be in saturation region. Okay, so this potential starts decreasing. You are somewhere here. So this VDS, if I take some numbers, say as 2, then I can see my this is the drain. So drain is at 2 minus 0 minus VTN is again 2, and my gate is at 2.5 minus this is 0.
Ma'am, actually, what is T1 and the T2, ma'am?
T1 is this transistor, T2
Yes,
is this transistor, PMOS.
yes, ma'am.
Ma'am, in this fourth region, actually T2 should go into linear region, no?
Mm, think T2 will remain in the same region, right? If I consider this potential, I think for this graph, this will be a valid value. So the VO is 2.
Because T1 is this NMOS and T2 is PMOS. So if we increase input, so PMOS will turn off, no. So saturated to linear it should come, no.
Uh, it will turn off here. When it is VSS minus VTP. It is greater than that potential, it will turn off. Here it will remain in linear. T1 will remain here in linear region. V0 is this, Vi is 2.5. For PMOS, VGS should be less than or equal to VGS minus VTP. I think, is this condition correct? So this will be in the saturation region, right? Is T2 fine now?
Yeah, it's fine.
This condition is correct, right? VGS should be less than. Instead of changing this, I have changed here. Or is it VSG? This should be plus. This should be VSG minus VSD minus VTP. So source it is at 5 minus gate it is at 2.5, should be less than or equal to, so drain is at 2 minus plus 2, this is 1 less than or equal to, this is 2.5. And then this is minus. So 3 plus 1 4, so this is in saturation region. I think now it is correct. The same way for this, the gate is at 2.5 minus force is 0 greater than or equal to VD drain is at 2 volt minus source is at 0 minus TN is 2. So 2 minus 2 is 0, which is it is 3 minus. But in this region T1 will be in linear, right? Yes, this questions are from week 1 previous year assignment and week 1 lectures. VGS. But I think from here it will start to come out of the linear region, but from equation I am also getting it is to be in region saturation only. No, it is in linear region, but I think T2 in saturation is clear for you now, right? In the region 4.
Yes.
In this region, the VO value is Vi minus 2. So, if I consider Vi to be 2.5, VO should be 0.5. This place somewhere. So, some potential near to this. So, if we take those values, I think this 2 is more. So, the gate will be 2.5 and the drain is 0.5 minus VTN is this region I will confirm and yes, it should be linear, but I'm not getting this coordinate values to show you in numerically. Is it? Yes. The pinch of condition, I think I have made a mistake. Yes, thank you. In this slide, I will repeat this. This is my PMOS, V out, VI. Pinch of condition, I have written something here. Yeah. Not VGS, it is VDS, VGS minus 1. This is connected to VSS, this is the ground potential. So, saturation condition is VDS should be greater than or equal to VGS minus VTS. Sorry, I made a mistake here. This is the saturation and VDS should be less than or equal to VGS minus VTN for in the linear region of operation.
What I was saying was that when input was increasing, then the PMOS will go like saturated region to linear region, right? Then off. So this T2 should go to linear region before becoming off. So it is in a saturated region only in fourth region of operation.
But if you apply the numerical condition, I think it will be like the based on the drain potential, it will be changing. So because I used some, I made a mistake here. Instead of drain, I took it gate potential. It is this one. So if I take this same values, then the drain will be 2 volt 0, which is gate will be at 2.5 minus 2. Like here it will be 2.5, so here somewhere it will be around say 2.6 minus 2. So this value will be 0.6, which is getting greater than 0.5. T1 will go from off saturation linear.
Okay, now I got it. From the numerical value only, we can consider this regions.
Yes, yes, yes. Numerical, and also like we know that here it will be in saturation and this range of potentials. Like we know VO here will be VI plus 2, here it will be VI minus 2. From that, by substituting the values and these conditions, VGS greater than VT will be giving the condition for on and off, and VDS, this will be for the saturation condition. I'm sorry, I have made this condition before. I have written this condition wrong. It is VDS greater than or equal to VGS minus VT for saturation. By using these two equations and substituting the like values of the potentials, you can get the region of operation. Is it clear now? Yes, I think
Yes.
you got the region. Yes. So now if I want to realize an AND gate in this pull down network, how can I connect in the pull down network? NAND gate. So this will be 1 and 0. So for pull up, if any one is on, also output should be 1. So A, B. But for this like discharging to the ground, both should be 1. So both A and B should be on to discharge to the ground. So this is V out. So if we have a circuit like this, A, B, C. So what will be the operation of this circuit? So usually here B and C are in parallel. So here the BC will be in series, and to this A is in series. So here to this A will be in parallel. So in this way we will design this pull up network and this pull down network. So, so what will be this logic operation of this gate? Yes, so A, B plus C and complement. So for this one, it is same A, B plus C the whole complement, right? No, here the values are changing. This is for this circuit. Can we try? Is C here and then A plus B the whole complement. To for this we apply the De Morgan's law, slightly modify this, and you will get A bar B bar plus C bar. This is option A. So if you are breaking this bar, the sign will change. That is from the De Morgan's law. And output of this circuit, so both this will give A dot B, this will be giving C plus D, and this will be into E. So this will be mistake. Correct. So this will be AB plus, because it's parallel, C plus D, and the common is E, like for this, the whole complement. It is, yes, option C. C plus D in and E, and then A plus B. The propagation delay, we have seen it up will be due to the speed of the transistor and the capacitors, and we don't, it's not related to power, and the rise and fall time, and it is the average of high to low TP HL plus TP LH average. So the option is 1, 3 and 4. So the next is we have whether like when interface a TTL logic to a CMOS logic. Say we have a CMOS circuit here. This is a CMOS gate. We have another CMOS gate here. And this is say V out. Here we have a TTL based logic. Now whether this interfacing is possible, like what are the things we have to consider for interfacing. So usually when the TTL is going to drive the CMOS, then current is not having any problem. Current level, there is no issue, as this will draw very negligible current here. So there is no issue with the current level, but VOH is less than VIH. So here, because of that, we will add one pull-up resistance here. From this and so this pull-up resistance value we will add usually say some 2 to 6K. And then when the CMOS is going to dry, that time voltage will not be having any problem, but the current levels will be a problem. So the IOL of the CMOS is actually very lesser than IIR of the TTL. So we will add some CMOS buffers so that we can increase. So like somewhere around this current we can derive this values. We can see that the VIH of a CMOS is around 3.5 volt, but the VOH of an TTL is around 2.4 volt from the data for a 5 volt supply voltage technology. And then for this one, VOL of the CMOS is 0.4, and which is very for the TTL it is minus 1.6. So to boost this, we will use the buffers. So coming to this question, the circuit.
No, once again, question 8, please.
This one.
No, question 8.
Question
Number 8.
number 8 is
7th question. That gate.
7. Which one?
Ma'am, I didn't understand this question.
Yes. These two are in series. So like if both are on, then only there will be a conducting path. So it will be like A and B operation. Final operation will be complement because of this is CMOS logic, because this will be not providing path to VDD, it is providing path to ground, and here any one is on, it will provide the path. So it is like OR operation, C or D, and with that E should be on for having a path to ground. Now this or this, any one C plus D E, if any one of the path is on, then we will have a path to ground. So this will be the logic, and this is providing path to ground, so it is complete. Now it is clear.
Okay, I got.
Yes. So now we have seen that when we are interfacing, this logic is a CMOS logic, and this one is the TTL logic. Now we have seen this TTL is going to drive this CMOS logic. So the circuit will not work because the voltage levels are different. So when we are having this TTL is driving, the voltage is a problem, so we need to add this pull-up resistance. So here there is no such pull-up resistance, so this is the answer. Any doubts? In the next class for the BJT, this condition when IB is less than IC min by HFE, then what will be the operation? This one I will explain, and then this CMOS transfer characteristics also once I will briefly explain. Because in this I have made one mistake. For saturation, VDS should be greater than VGS minus VT. And Yes, I see. Any other doubts? These two things I will.
I mean that gate question only there is one doubt.
This one,
No, previous.
8. Yes,
No, previous to this.
yes,
Yeah, this one. In that first VDD that to network up to V out that would not consider in this output that we would not consider.
yes. This will be we will consider. This will be opposite of like here A and B are in series. So here A and B will be in parallel. C and D are in parallel. So C and D will be in series here. And this was series with E. Now it will be parallel with E. So for writing the equation, you can take either the pull up or pull down. For pull down network, this will be the procedure.
So we can consider any of them.
Yes, it will be like this will be providing a path to 0, and the same way this will be providing path to 1. So
Okay.
here it will be
So either of them we can consider.
for writing equation purpose you have to you can take any one and then before you can write the equations. But for logic operation we need both pull up and pull down.
Okay.
Once you get the pull down network, then you can design the pull up by making the series to parallel and parallel to series.
Yeah, I got it.
Yes, yes. Any other doubts? Any other questions?
Where this recording of this session would be available for us.
We have shared, like you got any sheet, right? In that we will upload this in a YouTube and we will share the link of that YouTube in the sheet.
Okay.
And in the drive we will upload this PPT. Yes. Any other doubts? If no doubts, we can complete today's section. Thank you all.